Hi, my name's Trent Verhagen. I'm the National Sales Manager at FuseCo. Littelfuse, exclusive partner in Australia for protection relays. And today we've got the honour of having a guest speaker, Mark Pollock from Littelfuse. Mark is the Global Standards and Applications Engineering Manager at Littelfuse. And he's also participates in a variety of working groups for standards across the world, including Australia. Welcome, Mark, and thank you for joining us.
Well, thanks, Trent. It's great to be here and to be able to do this webinar. So I'm going to jump right in and start looking at the content here to make sure we get through it in time. Yeah, as Trent mentioned, we work with FuseCo here locally in Australia, and very excited to be able to have this chance to speak with you guys, with everybody here. So to start off, I wanted to have some introduction on, what is an arc flash? I think it's maybe some content that some of you have seen, but it's good to get a baseline understanding of what we're talking about. So when we look at electrical hazards, and specifically when you look at the data that's gathered from electrical incidents and what type of hazards are causing injuries, causing fatalities, we have electric shock. And so this is when somebody is coming into contact with something energized. So there's current going through the body that creates a shock. And arc flash is when you have a real sudden burst of energy that comes out when you have electrical current that is going through an unintended path. So typically through air, that is going to create a sudden release of energy. And an arc blast is really related to an arc flash, but the blast is when you have a pressure wave building up inside the equipment from, when components are changing from solid to being vaporized, it really creates an expansion of volume and can blast open the panel. So then there's physical parameters from the blast itself in terms of the panel breaking apart and things that could injure you. So what does that mean for some of the specifics about the hazards? So when you have an arc event, it's quite amazing how destructive that is. So that arc, and we're showing an arc just across two pieces of bus bar. When you have that arc, it generates a tremendous amount of heat. So that is getting close to 20,000 degrees Celsius at the point of arcing. And that creates a huge amount of heat that is coming out of the panel, as well as vaporizing those copper particles. And as each of those copper particles changes right from a solid to being vaporized, that expansion in volume can be up to 40,000 times. So you can see how it really generates a massive pressure buildup inside that equipment. And as that occurs, then you have pieces of the panel breaking apart and really being sent out like shrapnel. So in addition, all these components that are inside an electrical panel, they're not built or intended to be burned. And so there's a lot of toxic gas and smoke. And if you're standing in front of a panel and something happens, a human reaction for the first, when you first experience that, is to take a breath in, when you have something like that, an event like that. So then you're pulling in that smoke into your lungs and that superheated air that can also cause, internal burns, not just burns to your external body. So something to keep in mind, when you talk about an arc event, sometimes there's a thought of, well, we have all the regular electrical protection. We have circuit breakers, we have fuses. Why are these not providing protection from an arc flash? And when you look at these arc events, there is typically, or can often be, some resistance in that arc. And that means that the arcing current is often less than the short circuit current or the rated operating currents for the breaker or for the fuse. So you can have an arc that is continuing to burn, and even for 1 or 2 seconds, you've caused tremendous damage. But that arc that is continuing to burn over that 1 or 2 seconds, it can often be below those interrupting current ratings. So even though you do have fuses and breakers, they're not by default always going to pick up those events unless it is a 3-phase bolted fault or a bolted fault without resistance. So to put this into a little perspective, I have a couple of videos here, and these are high-speed videos that I have permission from Sandia National Labs to show. And if you look at the bottom left of the video, there's a time tracker that shows you, how many hundredths of seconds have gone through. So I'll just start the video, and you can see, how much heat and energy is created by that arc. And right now, this video is only showing you, moving past 0.5, 0.6 seconds. So all of this happens so quickly, and so much energy comes out in a very small amount of time. So this just helps to show, the magnitude of energy that is there in that arc event. This one was designed not to break apart, but just to show that energy in the panel, even escaping through any open parts. And again, this one is another look with a high dynamic range, and you can really see here those copper particles. So those are all molten, superheated, hot, copper metal particles that can cause, burning and, of course, cause a lot of damage to things that could be nearby. But the primary risk is that really can cause burns and be extremely hazardous to anyone who's unlucky enough to be standing in front. So I would expect that you've seen, a variety of photos of, aftermath pictures, but this is one example from a customer that had an arc event. And as you can see, it's complete destruction of the panel inside. And so for this particular customer, when they had to replace their switchboard and the downtime they were experiencing while they're waiting for the new switchboard, it was, almost close to $4 million Australian dollars in terms of the damage that was caused. So there's a very significant human risk, but there's also a very large financial risk in terms of interrupting the business and waiting for lead times for new equipment that could have been destroyed. So it has a very big impact on many things. Now, one thing that I wanted to add here as well is, we think about these arc events on large industrial panels, on large systems of thousands of amps. But, really, what is the arc risk when we look at smaller panels? So what's shown in the photo there is a combiner box that would be, a lot of 15 amp circuits, a 1000 volt DC bus. So what about these types of systems? Is arc flash a concern on some of these systems? So here's another couple quick videos. This first one was at 1000 amps. And again, a slow motion video here. So this is a 1000 amp connection where a wire was pulled loose. And so there was an energized circuit, and you can imagine a loose wire on the main bus that would just become disconnected, and it can create an arc. So this was at 1000 amps. But I think the next one is what was most interesting, that we did another test at 15 amps. And this one had the fuse intact in the fuse holder. So this was checking to see again, could a loose wire coming out of the fuse holder generate an arc? And so that's why you can see a string coming off to the right side where we were pulling out the conductor under load. And this arc is not as much energy and not as large as the previous one at 1,000 amps, but still a significant arc that could cause a lot of damage or injure someone. So what we're seeing on the right side of the slide here, is the current and the voltage that we were tracking during the test, and the plot on the top right is showing the light intensity that we were measuring from that arc in different positions in the panel. So that previous photo showed a few numbers. These were different spots in the panel where we were measuring the intensity level of the light that was coming out of that arc. So I'll talk a little bit more about the mitigation methods coming up on these future slides. But the goal of this testing was to understand, even at 15 amps, even when we have a fuse in place on that type of system, could there be an arc sustained at those current levels that would be hazardous enough to worry about, and that we could detect properly as well. And so it was a good experiment to show that it is actually enough to sustain an arc below the fuse current levels. Now, probably everyone has seen videos of arc flash events before and talked a bit about it, but we have to understand, if we're trying to reduce the hazard and we want to reduce the energy that could come out of an arc flash, we have to look at what are the things we can control. And so the arcing current is a major contributor, and really that has to do with the short circuit current coming out of the system, the bus configuration. So not only, the direction that they are oriented, as well as, the gap, whether or not they're insulated, and the voltage. And once we figure out that arcing current, the ultimate energy that comes out depends on the time duration and how far away you are from that arc event. Now, the arcing duration I have highlighted because that's really a focus of, if we want to reduce the arc in electrical systems, this is something that we can work on to try to make a safer system, reduce that arc energy by interrupting faster, having a faster clearing time. So there's a couple slides that are a good reference on codes and standards, just to kind of base the discussion. It's not a deep dive. I know there's a lot of material you could go through on this topic, but just want to give a brief introduction on a couple items here. And, a good question to start off with, is it mandatory that you have to take some sort of action to reduce the arc energy? And I would say that depends where you are located in the world. There's a few places that are starting to make it mandatory in the electrical code. So in the US, it's been that way for 10 years. And in Canada, just recently, 1 year ago, adopted the same requirement that any system 1,200 amps or greater does require some form of arc energy reduction. Brazil has put together a standard that is aiming towards making arc prevention requirements as well. And there's other countries beginning to move on that. As far as I'm aware, I'm not sure that that's mandatory in the Australian wiring rules, but this is, the way a lot of the electrical industry is pointing. Now, another good base question to talk about, we talk about arc flash, but what's the difference to arc fault? Because we hear about arc fault protection and arc flash protection, and are these the same? Or how are they different? So when we use the term arc fault, typically we're talking about the current-based detection, And a lot of those are installed in household or light commercial applications that is looking at the current signature. It's measuring the current, looking for a particular signature in that current to determine that there is arcing occurring somewhere downstream. So then you can have a device that's installed in the switchboard that's able to see if there's arcing on that circuit, and really designed to detect arcing that can occur inside walls, or if there's a cable that's been damaged. It's easy to think about wiring that's in a wall, and someone goes to later on hang something on the wall, and they put a nail through and they put it in the wrong spot and pierce the insulation of the cabling. So this is really what is generally referred to as arc fault protection. And when we're talking about arc flash protection, in this case, we're looking at other forms of detection. Typically light is one of those. Current can still be used as well, but we're looking for those high energy arcs. And these systems are usually installed at the location where the arc detection is desired. So this is more used on the industrial space, and where a fast reaction time is really incredibly important. So this arc flash topic is what we're talking about here today. And there is some good standards to review on these topics under the IEC banner. 63107 talks about integration of arc flash detection systems into switchgear, into 61439. There's another document being worked on right now for a revision, 61641. And there is also a product standard for arc flash relays, IEC 60947-9-2. So these provide a good basis for some of the arc flash topic we'll talk about here in the next few slides. So if we want to try to reduce the energy, we need to understand how to calculate what that energy is. And when you do an arc flash hazard analysis, there's lots of service firms out there that can do this kind of work. You really need to understand, you're trying to quantify what is that energy exposure so that they understand the arc flash protection boundary and what PPE needs to be worn. So if you see an arc flash hazard label, the energy is expressed in calories per centimeter squared. So that's what we would call the incident energy. And of course, if you want to select the right PPE to provide protection, personal protective equipment, you would use equipment that has a rating, equal to or above that incident energy that is available in that panel. There are a few different standards out there, but really what I find to be typically the most common guide or standard for actually doing the calculation is IEEE 1584. And so 2018 is the current edition. It's based on many real arc tests, and then taking that data and synthesizing it down into a formula that you can calculate what is the anticipated incident energy, based on all the parameters of the system. So there is a new revision that's just starting. This work continues to evolve over time, and as more tests are done. So another revision is just starting now. So that will be a number of years till that's published. But just as interest sake, to let you know that that revision cycle is starting again. So once we've calculated what the incident energy, what the risk is, then we start to look at, okay, how can we mitigate this? How can we reduce that energy? And the hierarchy of risk controls is often talked about, and it's a fantastic way to frame, looking at the different things we can do. And I included a link there, to the WorkSafe Victoria site, but there's many resources that talk about prevention through design or safety by design. But this hierarchy of risk controls is really the standardized way of looking at these. And how can we, we'll say, do the most good? How can we provide the best mitigation? And by moving up this pyramid, you might sometimes see the pyramid the other way around as well. But by moving up the pyramid, that's how we get the best effectiveness. So when we start looking at engineering controls, substitution, elimination, these are things that are very effective. The other parts of the pyramid below are still very important and in fact might be mandatory, but these are ones that can still be affected or reduced by human error. Whereas once we move to this top section, that's really where we get excellent take up, or we'll say effectiveness of the control we've put in. Now, one side note, as we start talking about the different ways for mitigation, one that maybe not everyone thinks about is the earthing of the system. Now, if you look at a number of different sources, what I've linked here is a power systems book by Dunkey Jacobs, but there's research out there that talk about what type of electrical faults, in terms of statistically which one is most common. And an earth fault is by far, whether your number is 85 or 90 or 95, it's by far the most common type of fault. And this is really by design. Now, if you think about that, if you have a system that is solidly earthed, so you have a secondary of your transformer that has an earth connection on the neutral, when you have a phase to earth fault, like we're showing here in the slide, that current for that fault is really only limited by what the transformer can put out, the transformer impedance, as well as the resistance that's in that fault. So if the resistance of the fault is very low, then you could have a very high fault current. And that could certainly be a potential arc flash. Now, in some applications, some industries, such as data centers, mining, and some other processing plants, are beginning to use a neutral earthing resistor. So that's this resistor here connected between neutral and earth. And when you have a resistor in this location, when you get the fault that is occurring, now you have another resistance that is limiting that fault. And what's common in these resistance earthed systems is you would have that limited to a quite low value, maybe 10 amps or maybe 5 amps. So you've virtually eliminated the chance of that earth fault becoming an arc flash because the current is so low that it's not able to sustain that. So this is something maybe not everybody thinks about, but this is one system design that can contribute to reducing the chance of an arc flash. Now, just to be clear, if you have a phase-to-phase arc flash, the resistor is not going to limit that current. But as you saw in the previous slide, if 90% or 95% of your faults are earth faults, this goes a long way to reducing the likelihood an arc event will occur. So for those of you that maybe haven't seen an earthing resistor before, this is just an example at medium voltage where you see the resistor coils, mounted on insulators in an outdoor enclosure. So it is one thing to keep in mind in terms of system design. So I'll go through a few other topics here and just talk a little bit about how they can reduce the arc risk or the arc energy. So another substitution method of, we'll say, changing the electrical system is, when you're doing that design, instead of having, one massive transformer that's powering a very large amount of equipment, of course, it is possible to then divide up the system a little bit and have 2 or 3 smaller transformers. So then there's a smaller amount of energy that's available to feed into an arc flash. So that's, again, can be a very good way of approaching the system design. And of course, it's very effective because once you've made that change, that's the way the system is. It does have a cost factor. So depending on, many parameters, that could have a cost adder. And one thing to keep in mind is, even if we're moving to smaller transformers, each of those smaller systems, still might be possible to generate a lot of arc energy and might require arc mitigation on each of those systems as well. So this is still a good idea in many cases to do this, but keep in mind it may not stop you from having to have additional arc mitigation on each of those systems. So another one that's has been quite popular is looking at arc resistant switchgear. So this is building the switchgear so that when an arc event occurs inside, that energy is contained, and the panels are built to not have the doors open, and it redirects the energy. So the photo perhaps doesn't have a great show of the plenum, but then normally this energy would be directed upwards into a plenum that would be redirected outdoors, or somewhere where there's a designated area that people are not going to be there. So it redirects that energy. So here in this picture, we see a plenum on the left side, with an opening that would likely be connected to another set of plenum there. So this does a great job of protecting personnel that might be standing in front of the equipment. Of course, as long as the doors are closed. So if somebody's doing maintenance on the panel and the door is open, then that arc mitigation is just not going to be there. One other cautionary item is, of course, if anyone has tried to do any modifications to this equipment or change a component, they may have compromised the original manufacturer's arc mitigation measures. So that's something to be aware of as well. And on the last 2 bullets at the bottom, while it does contain the energy and make sure that it doesn't get released out to hurt someone who could be standing in front, it is not actually reducing the energy. And so that means the equipment inside is still likely going to be destroyed or have some significant loss. And if you're in an area where there's a code requirement to reduce the energy or reduce the fault clearing time, this is actually not going to satisfy that requirement. So it is an excellent thing as far as safety is concerned, but it still is going to have damage to the equipment in the case of an arc, and still may not meet the requirement to reduce the arc energy. But it's something that could be done perhaps in concert with other items that we'll talk about here. Another item here is an engineering control when we look at zone selective interlocking or bus differential protection. So these are protection relaying schemes or breaker schemes that you can have logic connections between them that can have some very fast acting protection. So these, when you look at bus differential as an example, it's measuring the amount of current coming into a junction and what current is coming out of that junction, on 1 or 2 branches, or however many branches there are. And when we look at zone selective interlocking, that is, having breakers or relays that talk to each other, and when they see a fault in a certain zone, they very quickly with communications decide which device is going to trip. So these provide fast acting tripping, but they do require some engineering in order to make that happen. So it can require, matching breakers from the same brand or the same series that can accomplish this communication, or having matching current transformers. So this can sometimes be a little bit more challenging in a retrofit. And it might dictate, needing to use a certain brand of equipment or have matching brand. And as well, when you are doing some of this fast acting protection with the bus differential, it can, we'll say, interrupt your normal selective coordination, because now you need to react faster and you're not taking that coordination into account. One other engineering control is arc flash relays. So this is something that installs into the equipment and uses light sensors to see the presence of an arc. And once it sees that arc, has a very fast acting trip signal that can trip the breaker. So we mentioned before that, an arc can often be below the instantaneous zone of a breaker. So this is a way of seeing the light from an arc and providing a fast trip signal to the breaker to make that interruption happen. One advantage is that it's independent of the inrush currents, so you don't have to worry about the settings and making sure your current settings are above, those inrushes. But it does also disrupt that selective coordination, because now you're just tripping based on light, independent of what all the devices might be set for current. One thing that is really good about the arc flash relay, in my opinion, is that it has quite a few self-check capabilities that allows it to be installed quite easily, but makes maintenance activities simple over the lifetime of the equipment, because the relay can self-monitor its ability to detect light. One note is that there may need to be some limitation of use of high-intensity flashlights, or utilize a current inhibit signal that looks at both current and light to pass the trip signal forward. But the bottom line is that arc flash relays do provide solid incident energy reduction, and they're something that can be quite easily applied both for new equipment and retrofit. And the last couple items here, once we move down out of engineering controls into administrative controls, one that is somewhat common is a maintenance mode switch. So different manufacturers have different names for it, but this is a switch that can be fitted with a circuit breaker. And essentially, when you turn it on, it puts the breaker into a very fast acting mode. And so then it reduces that energy rating while it's in that fast trip mode. Now, the issue that I've seen in some cases with this switch is that it's still subject to human error. So it relies on somebody flipping the switch into maintenance mode before they, work with the panel. And it also requires somebody to remember to turn it back into operating mode after they're complete. So it is something that relies on that process or that human element. And the other thing that can be a little bit confusing is there typically would need to be two arc flash labels, now as well, because there's a different arc flash rating when this is engaged, and there's a different arc flash rating when it is not engaged. So that can be a little bit confusing, and again, subject to somebody looking at the wrong number when they're selecting PPE and not matching, what the switch might be set to. And finally, talking about PPE, this is another administrative control, but remember, the PPE is really the last line of defense, and it's not doing anything to reduce the arc energy, but it really should be complementing the other actions that you would have in your electrical safety program. So it's still an essential part of what you need to do working with the equipment, but using those other measures we talked about can be a way to reduce the arc energy and therefore reduce the size of the PPE in the suit you need to put on, which can make the work more efficient as well. But just getting the PPE is not really doing anything to further the safety or reduce the energy. That's just the minimum bar. And looking at some of these other actions that can be taken is really what brings in enhanced safety. And remember, with the PPE, when you get a number on the suit, if it's a 40 calorie per centimeter squared suit, that doesn't mean that in 100% of cases, every person will have zero effect if they're subjected to that arc. There's still an element of some burn that can come through the suit. So it's something that, looking at ways to make the system safer is really going to move the needle in terms of having that electrical safety. So I wanted to have a few separate slides talking about arc flash relays in particular. I do think they're one method that is quite accessible in terms of installation, both for new and retrofit systems, and talk a little bit about how they work and how they accomplish their goal of reducing the arc energy. So, as I mentioned before, the way the arc flash relay works is by having light sensors that are installed throughout the cabinets, whether it's in the bus bar compartment or the breaker compartment. You would put the light sensors wherever the arc protection is desired, wherever those locations are that could create an arc. And these relays are designed to have an ultra fast response time to that event. And, there's many relays on the market that can do that as fast as 1 millisecond response time. And again, when you look at the products on the market, there's a lot of different options that can provide a variety of capabilities, whether someone's looking for something relatively simple or more advanced. Now, I mentioned that one thing with arc flash events is that because they're based on light, if there's high intensity flashlights or other high intensity light sources that are shone inside a cabinet, that can potentially be something that could trigger the relay and trigger a trip event. So if that is a concern, a lot of relays on the market offer the ability to pair a current measurement. So then you would need to see the light plus elevated current, above a certain level before you would proceed with the arc event. Now, one thing to keep in mind, if that's something that is done, you have to be a little bit cautious where you set that current minimum level, because you don't want to set that, too high. Otherwise, you end up in a situation where you could have a very resistive arc at low current levels, but the relay is not responding. And these devices are something that's interesting because they're based on light, is that they're really applicable to both AC and DC types of equipment. So that can be one advantage of looking at arc flash relays as a mitigation measure. Now, the sensors themselves that are used to measure light, typically when you look on the market, there's two types of sensors. One is a point sensor, and as you would see, they're installed in a single point. So they detect the light in one fixed location. And the benefit to that is that when your relay triggers on an arc event, you can very quickly know exactly which location that arc occurred, because you know which sensor has generated that trip. So that's one advantage. And these typically would have some sort of self-check capability as well, just to make sure that if that cabling is cut from the point sensor back to the relay, if that becomes disconnected or cut during the life of the equipment, that you would have the ability to give an alarm. And again, depending on the manufacturer, some of these might use copper cabling, and some of these might use fiber connections from the point, back to the relay. And that just has an impact on, how you install that in the panel. The other type of light sensor that is common is a fiber optic. Some call it a fiber optic rope sensor. But this fiber is a specially designed fiber to bring in light into the fiber and then channel it, down the fiber to be measured at the other side. So this type of sensor, is nice because it covers a very wide area. So with a single sensor, you can then have something going down the entire length of a bus bar. So that could be, 10 meters, 20 meters, or even longer with one single sensor. So that also provides benefits if you have cabinets that are very tightly, very densely packed. Taking a fiber and routing it through different parts of the equipment can allow you to cover a large area with only one sensor. And again, some form of self-check is recommended when you're looking at these fiber sensors, just so that you can make sure that there's no damage or cut, in that fiber as well. Now, I'm not going to go through the mechanics of this in detail, but when you look at how the arc flash relays are applied, this is something that can be quite flexible to all types of systems, and depending, however, the customer would like to have that installed. So, when you looking at, this system here is showing a tiebreaker with 2 incomers on the bus, and arc flash relays, as I mentioned, are nice because they're flexible. They can be set up in order to trip, a particular feeder if there's an arc detected on that breaker, on the cable output of that breaker, or it could be set up to automatically trip that half of the bus, trip that incomer and trip that tie break. Or you could also decide to just simply trip everything when you see an arc. So the relays can be quite flexible depending on whatever the need is for the application. So a few considerations when you're looking for arc flash relays on the system. One of the main things you want to look at is what is the tripping time. So when you look at reducing the energy on the system, what would you like that reaction speed to be? As I mentioned, there's devices out there that are, 1 millisecond response, some that are 5, some that can be more. And that's one thing to keep in mind when you're looking at sourcing a relay. Also, the type of output contact. So those fast-acting 1 millisecond trip outputs are often not a mechanical contact. They could be an IGBT, they could be some form of contact in order to get that fast operating speed. So if you need a mechanical contact, to engage with your trip circuit, then that's just something to be aware of when you're looking for the relay. Another is, what are the safety functions of this relay? So I show redundant circuitry here. So whether the device is using redundant circuitry to provide that safety, that solid performance when it comes to the analysis of the product under component failure. Is it SIL rated? What are those things in terms of the redundant circuitry and safety for this product? The next one on the list here, I have health monitoring. Once you have this system installed and you have your light sensors, you want to make sure that this system is continually operating all the time, and that those sensors are being actively self-checked so that they're not in a situation where the cable becomes cut and it's not, the system is not alarming. So having some form of self-check on those sensors, can be a pretty important item. And even look at, what does the product provide for monitoring connections on the output as well? Or if there's a link to other devices, how is that link being monitored? How are we making sure that this device is operating with an active self-check for all the connections? So next, if we're talking about the light detection, that's the critical part of the relay detecting the arc. So making sure to understand, how is this relay detecting that? What is the light intensity that's needed to create this trip event? And just being comfortable with that. So that's another thing, understanding how that's done. Another item here is the boot up time. So this is something that maybe not everybody thinks about, but once you are doing maintenance on a system, and so it might be totally shut down, when you come back online, that's maybe one of the times where there could be issues. Maybe somebody forgot the earthing straps on the phases, or of course, the classic example is somebody left a wrench or some piece of metal laying around or touching some of the phases. But when you're coming back online after maintenance, that could be a time when you have a higher probability of an arc. And so when the equipment is being energized from a dead start, what is the boot up time on the protection devices? How long is it going to be that they can detect this arc, after this energizing time? So that's something to be aware of. When you look at your tripping scheme, what type of upstream tripping do you need? Do you have upstream breakers that you can go to in the case of a local breaker failure? What if the arc is inside that breaker that you would normally be trying to trip? Or we'll say at the load terminals for that breaker. Tripping that breaker is not going to stop an arc that's at the load side, at the line side terminals of that breaker. So do you need that ability to trigger additional breakers or trip upstream in the case of the first breaker not responding after it's given the trip signal? Another one, looking at the data logging capabilities. So when you look at what investigation might need to be done after a trip event, how much detail is there provided in that data log? And is that going to be enough information to help you look through and investigate that event after the fact? And is a waveform capture something that's required? That's, not a standardized function in arc flash relays today, the same way that it is in a lot of the feeder relays using, Comtrade or other platforms, but being aware of what data is available. And the last couple here as well, when you look at zone tripping, I showed the big diagram of all the breakers and how you could use relays to start to create multiple levels of zones. So an important aspect to looking at these relays is, what kind of scheme do you want in your system? Do you really want to try shutting down only the affected part first, and then have some delays to move up to the next zone if needed? Or do you want to just shut everything down as quick as possible? And finally, the current detection, the conversation, about that needs to be, is that required? What is truly the likelihood that somebody would go in with a high power flashlight and cause an issue? And if so, then, adding the current inhibit. But keep in mind, then the conversation shifts to, well, how much current do you want to use as your level where you're going to say an arc trip should proceed? So these are some of the considerations that should be reviewed if you're looking at an arc flash relay. And as I mentioned, the waveform capture may not be something that is standardized. And so I wanted to show just at least one example of what that could look like, just because maybe not everyone has, be able to visualize what that would be when you're talking about light. So to finish off, I have a few photos. I think it always helps to show that context of how those kind of products are actually used in the field. So here, just a couple examples of point sensors installed in different types of equipment. So on the right side, looking at the terminals on a transformer, and on the left side, looking at a big, large piece of bus there as well. So that's putting the point sensor into the bus compartment. And here's another few examples of a fiber sensor. And so here you can see, the fiber can be brought through multiple sections of the equipment and allows you to cover quite a bit of distance really with one sensor. And a common question is, well, how do we bring that fiber properly, from one cabinet to the next cabinet or one section to the next? And it is recommended to use something like a rubber grommet. You can see in that top photo that is able to, at least partially seal between the compartments and hold the fiber without providing too much force onto the fiber that could, we'll say, damage it or reduce the light coming through it. So here's another example of how the fiber can be put into a bus bar compartment. So this is a plastic circular tube there that has anchors on it. So this can also be used to guide the fiber through the compartment without having to try to pinch on it, in a strong way. So this is another great example of showing how that fiber can be routed down through the bus bar compartment. And just to show one more example on that, I mentioned earlier that the fiber is also able to be routed through cabinets that have a lot of pieces of equipment inside. And so this is showing how inside where you have, a breaker, you're able to take that fiber and look at the line side terminals, the load side terminals, and bring it through various parts of this central distribution panel so that you can cover quite a bit of space with even one sensor. The normal recommendation would be to try to have line of sight to the areas where you are most concerned about the arc. So here we would like to have line of sight to the terminals on the line and load side, as well as, where there's other cable connections to the bus and things like that. So the fiber sensor does make it flexible that you can cover those, with a minimum number of sensors. And I've mentioned here by the arrow to watch for the bending radius. So again, depending on, the manufacturer should specify what their bending radius is on that fiber. Because if you take that fiber and you bend it too much, you end up with light that can escape from the fiber. And so therefore that reduces the effectiveness of the relay, and it's not performing, to the specifications. So that's something to be aware of as well when you're doing the installation of those fibers. So those are the slides we had prepared. And, if there's any questions about that material, certainly very happy to engage with anyone and answer questions on this material or anything related. And what we've put for contact information in the bottom left is, and we mentioned that FuseCo represents Littelfuse here in Australia. So they would be the great local contact point, for any questions that you might have. So hopefully this was able to provide some interesting material and talk about ways of doing arc mitigation, and talk a little bit about how, arc flash relays, which I think are one really interesting way to do that, can be put into the system, and some of those considerations to look for. So thank you very much for your time, and have a great day.